Okay, good morning to everyone on Zoom. Thank you so much for joining us. Welcome to the latest iSense Distinguished Seminar. And I'm going to pass it over to you, Jordan, to introduce our speaker.
Thank you, Matt, for making the drive down. It was a heck of a drive, and especially having to come all the way to South Florida, you know. But yeah, so Matt, you are a professor of, and correct me if I'm wrong, this is from your website, but you're a professor of forest water resources and watershed systems, University of Florida. You joined the School of Forest Fisheries and Geomatics Sciences in 2006. Your primary area of research is watershed hydrology and biogeochemistry. No, that's accurate. You do a lot of work on wetlands, and you have affiliate status with IFAS, so that's the Agricultural Extension Office, IFAS Soil and Water Science Department, School of Natural Resource Environment, and Center for Federal Policy at UF. You got research funded by a whole lot of organizations: NSF, DOE, Army Corps, FDEP, and all the water management districts. So once you do work in this realm, having work funded by all 5 water management districts is pretty impressive.
In one project, in one case.
Yeah, to networking capacity there. More recently, you're the director of the UF Water Institute. It's from last year, I guess.
Yeah. Coming up on my 1-year anniversary.
Yeah, so it's a pretty big career step there. Pretty big honor, I guess. And I just met Matt actually last year. You were the lead on a massive lift to basically develop a chat GPT for the state of Florida water. This involved tremendous number of collaborators and stakeholders, all 12 members of the state university system, well, 11, but we're kind of it's a long story, and that was a huge lift, and I was really impressed with the work you put into that. And I loved your modest and kind of humble attitude, despite being obviously a rock star. So I'll pass it off to you. Again, thanks for making it, Brad.
Yeah, I appreciate the invitation. I really do. And I'm going to spend a little bit of time in the seminar kind of talking about the Flow Center proposal, which is what Jordan was talking about, which is when I really met Jordan. And because for me, one of the objectives of coming to events like this isn't just to kind of toot my own research horn. It's really to kind of to build bridges with programs. And as part of the Flow Center proposal, which, as Jordan said, was 11 of the 12 state universities banded together to say we can solve these constraints in the water space with regards to data harmonization and data availability, but also beyond that. And I'll talk a little bit about that enterprise right now. But one of the things that it was revealed to us is that there's an enormous amount of capacity distributed across the state university system that isn't, sort of well known outside of each of the universities, and that is, I think, partially why I wanted to come down here to get to know iSense a little bit. I just got an outstanding tour. Thank you, man. And just to understand a little bit about what you guys are doing and the ways in which we could collaborate. And so I think that's a really important piece of any administrator's job. And so the Flow Center, the Florida Water Center, was a solicitation from the Florida Council of 100. So these are some very influential business people that said, listen, water is kind of it's well invested in, but it also needs some help to be sort of fully realize some of the data potential. And so I pretty quickly realized when I saw the solicitation, this was in February of 2024, that there was no way any one university was going to be credible at doing what they were asking to be done. And so reached out pretty right away to a bunch of partners, and 11 of the 12 state universities said yes. And those are listed here. And the idea was we would have a lot of regional specificity with regard to understanding about the data availability in South Florida or Central Florida or the Panhandle. We would have contacts and partners, and collectively we would be able to really mobilize the data in service of all the various sectors that are utilizing data. So that is, and harnessing not just the data expertise, but also all the brains that have been thinking about how to interpret those data. And so these are all the partners. We have some private partners as well. Okay, can you just click on the screen real quick? Because yeah, just click right there. There we go. I'll let me advance. So we have some mission areas. I mean, the main one was that one up in the upper left, the water source, which is basically a data catalog inflected with AI capability to enable lower barriers to search. But in my opinion, the data are actually in relatively good shape, modest shape, I'll call it in the state. But the status of the legacy of information that we've built, all the gray literature, even all the peer-reviewed literature, is really quite disastrous in my estimation. I wrote a report. I know the date that it was published. I know who was funded to do it by. I couldn't even find my own report, let alone other people's reports. And so this waterworks idea is that we're going to be able to mobilize information from the gray literature. We're going to be able to provide a searchable expertise database that's going to connect you as a researcher with a certain portfolio of expertise to users outside the universities, but also to partners within universities. And I think that'll be a real catalyst for collaboration. Convocation was a big part of what the Florida Council wanted to see happen, which is that we have meetings and we convene meetings that are either big picture water policy kinds of meetings or sensor design and deployment kinds of meetings, and that there would be this sort of smorgasbord of meetings that could happen across the state that would build the capacity that exists in the universities, build it out into the private sector, and build it out into the workforce through students. Thought leadership was a big piece of it, and then trying to convene educational programs was another big piece of it. All these are kind of the aspirational vision, and I wish I could be here today. Like, it's funded, we're ready to go. Let's, all we're doing is signing the final MOUs. We're not quite there yet. This is a big ask. It's $180 million over 10 years and distributed across all the universities. There's a lot of questions about governance. There's a lot of questions about funding and accountability and duplicity or duplication of effort. All of those are why we're sort of still en route towards that. Wrong direction. I'll just say that the model, the conversations that I've had while I was at Harbor Branch yesterday and then this morning, it's just evident to me that there's a lot of data collection enterprises that are going on at FAU, that are going on by the state, that are going on at the level of the county. And the idea of the sort of centerpiece of this flow center proposal is data discovery, evergreen access, so that a user doesn't have to go to 18 different providers, that they're enabled to discover and ultimately utilize data. Also with the notion that benchmarking those data sets, the flow center, the Florida State University system has essentially blessed this data set as curated, and that really, I think, sets a launching pad for people to start to apply that information in a way that we're all sort of playing from the same facts. It's a modeling platform. It's also the biggest part that Jordan really brought a lot of intellectual capacity to the proposal was this bottom bullet here of the Internet of Things, where the idea being that we're on the cusp of this, the sensors are increasingly replacing the conventional historical way that we interrogate the water systems, and that we need tools to enable that across all the different providers. So that's the sort of core idea of the Flow Center. I'm going to transition from like that because honestly, I don't have much more information for you other than that if you want the 200-page proposal, and I'm happy to give an update, but we don't have any money yet, and I'm guessing it's at least a year before we're having those sorts of serious conversations. So I wanted to spend the rest of the time kind of nerding out about my own interest in sensors, which is on the user side, right? I have been very lucky to be sort of the recipient of some early data series, and I'm a hydroecologist by training. I was trained as an engineer, but then did a lot of ecological system science for my PhD. And the sensors were just a new way of thinking about old problems. And so I titled the talk, sometimes you can learn a lot, observe a lot just by watching. That's a Yogi Berra quote for those of you who followed America's greatest poet. And the idea is sort of trying to connect the dot between sensors, which is the mission of iSense is to fabricate, deploy, and then curate the data from sensors. And for me, I'm more interested on the user side. I'm a client in the sense of I'm a ecological theoretician. I do sort of thinking about function, and I want to connect the dots for those two things together. I spent a lot of time trying to make this happen. So this is sort of the vision of the way the world works until you have high frequency data, right? And so what you start is a very blurry view of the world, and what a sensor enables you to do, at least in my world, is to ask questions at spatial and temporal scales that you couldn't before, and really detect dynamics. And that's been the pitch that we've had in the literature, in the papers that we've written. It's also been the pitch. We've done a number of trainings, national level trainings about this premise that there's a lot to learn by asking and interrogating data sets at finer scales. So this is Yogi Berra. Sometimes you can observe a lot just by watching. There's a famous paper from 2004 by a guy named Jim Kirchner, who's a really well-regarded hydrologist, and he basically said, listen, the title of the paper is high frequency wave of the future, right? That the way that we've collected data to date is usually at best monthly grab samples, maybe in some really excellent locations, but prior to the 2000s, we might get weekly data. But if you have hourly data, now all of a sudden you're watching the unfolding of the hydrological system in a way that you just didn't see before. And so surely embedded in that panel D there is all sorts of information that's going to make us better stewards, better, better understand our watersheds, and by extension be better stewards of them. And that hypothesis is deeply embedded in this document. This is the Blue Book. This is for hydrologists. This is like for the students out there, 2012. They wrote a version of this back in the 1980s. The 2012 version is a re-update, and it's really like a roadmap. What is the things, if you're a student, what are the big questions you should be thinking about in the context of hydrologic science? George Hordenberger is the lead author. He's a National Academy member. And the grand challenges that they articulate in this book are, how do watersheds release stuff? When, where, how frequently, under what circumstances? How do the aquatic ecosystems to which those watersheds drain, how do they respond? And can we automate the detection of that? And can we automate our understanding of how river networks more broadly retain the things that would ultimately end up in places where we don't want them? And really the main contention that they say in this treatise is that we now have the ability to align the timescales of the ways that we think about weather data and the ways that we've thought about water level data, water quantity data, with water quality data. So now all of a sudden the solutes are sort of matched in terms of their time. It's a really exciting document because for me as an assistant professor, right, they put like 2 figures from papers that I'd written in this like seminal, this is what students should be thinking about document. I'm like, oh, that's cool. George Hordenberger likes my work. And so that's what I'm going to talk about for most of the talk here today is, what are the things that we've learned by applying the logic of sensing technology to ecological questions. I'll start by the kinds of data sets that people just get kind of verklempt about, right? These are the kinds of things that weren't able to do. This was from a workshop that I led back in 2012. These are coastal data, right, where new sensors to measure phosphate, ammonium nitrate were coupled with water level, and now all of a sudden you could just see the breathing ecosystem. The whole ecosystem's dynamics were revealed. Now this is a tidal ecosystem, so obviously there's a lot going on with water level, but there's also sort of the coupling of that time series to rainfall. And it's a very exciting prospect that embedded in these signals is information that's going to make us understand the status and trajectories of these ecosystems that we're trying to manage. So I'm going to sort of put a little, every time I think that there's like, wow, sensor epiphany, Yogi's going to show up. So there's Yogi Berra scratching his head. All right, so I'm going to talk about 5 examples. I'm going to try to do it quickly, but each one of these is a labor of love. There are papers that I spent lots of time with students and myself pondering. I want to talk a little bit about how we use sensors to try to decouple what's happening in rivers from what's happening in watersheds. And it's a really, I think, interesting and useful story. I'm going to talk about the breathing river analogy, which is these spring-fed rivers in northern Florida that are really outstanding laboratories for applying the logic that I'm describing, taking sensors to try to understand rivers as ecosystems. Changing the reference frame of the sensor. You guys, this is old news to you guys, but most stream ecologists, most river ecologists think about time series. I deploy a sensor and it collects a time series, but the idea that these sensors can be deployed in a Lagrangian framework where they're tracking a parcel of water as it moves through an environment is actually a different way of thinking about it, and it reveals a lot of interesting things. just for Jordan, because I know he does a lot of benthic flux work, some work that we did using sensors in deployable boxes. And then I'll come at the end to sort of a cautionary tale, perhaps, about how the enthusiasm for sensors is, I won't say misplaced, but we need to be mindful of what questions we're actually trying to answer. So those are the 5 things. I'm going to start with this signal and the noise. And, any watershed is a multifaceted, multi-use incubator, right? It's a filter that has inputs of rainfall. That rainfall is acquiring a solute signal from a whole variety of different land cover types, forests and fields and cities. It changes as it passes from the small headwater streams through the river order to river outlets. It might rain in one part of the watershed and not another. And so when you're looking at the signal of some chemical solute at the outlet of the watershed, understanding what you're looking at is actually really hard. How old is that water? Which land uses have been contributing to the signals that you see? You have the convolution of hill slope processes with channel processes. What is this signal? I have this time series, but I have no idea how it came to be. And there's a lot of I think, deep theorizing about trying to work backwards from those signals to understand something about the watershed. So we've spent some time deploying sensors. This is data from a small 3rd order Blackwater Creek in North Florida, where we have discharge in black. It's ranging over about 3 orders of magnitude. And the gray line there is a continuous phosphate sensor. It's cycle Ps that are a giant, up to now, have been a giant part of the Erlon deployments that Harvard Branch is putting out there. So there's all this very interesting dynamics that are revealed that when you have quarterly grab samples, you just wouldn't ever see. I'm not sure that the answer to the question, is it worth it, is just like, oh, look how pretty the dynamics are. I think there's something to be learned here. And if we zoom in, we start to see some interesting behavior. And in particular, this inverted covariance between the changes in discharge and the changes in the stream chemistry. When discharge rises, all of the water that gets into the stream is bypassing the high phosphorus sources, and so consequently the phosphorus concentration goes down. We can zoom in a little more and we start to observe diurnal signals where the phosphate concentrations are actually varying over 24-hour time signals. And so what you have are these interannual patterns, annual patterns, event scale patterns, diurnal patterns, all convolved and superposed on top of each other, creating basically an interpretive mess. And so how do you go about trying to extract all that? The idea for us has been, my lab is interested in the processing of solutes in river ecosystems, right? But if I look at these time series, these signals, deconvolving the hill slopes and the watershed from the stream is nigh impossible. It's very difficult to attribute variation to one thing or the other. And so if I'm interested in the stream ecosystem signal, I need some tools. Well, one tool is spectral deconvolution. So thinking about like Fourier transforms, right? So we take a time series of, and these are data from Jim Kirchner from a very small, like about a 5-acre watershed in Wales, where they've been monitoring the solute composition exiting the Plinlimmon watershed for 30 years, right? Initially every 7 days, and then later every 7 hours. And so they've constructed this extraordinary time series of solutes basically across the periodic table. So you don't very often see time series of cobalt in streams, for example, but these are all grab samples. There are no sensors to speak of. Take these time series, and the theory is that that basically the watershed serves as a filter, and it receives a white noise signal in the form of rainfall. So rainfall is basically a white noise signal that has, for the people in the room, basically a flat line in spectral space. That is to say that spectral power is uniform over all frequencies. And the watershed filters that signal, and it filters the signal in such a way that the damping is inversely proportional to the frequency. So you get this very coherent linear scaling. This is what they call fractal scaling. And what Jim and his colleagues have pointed out is that this fractal scaling is ubiquitous. It's true across every single solute that you ever look at in these small watersheds. And so what's happening is that the hill slopes, it rains on the hill slopes and they pick up solutes, and those solutes are transported at very, very different velocities that follow a long-tailed gamma distribution. And that distribution creates this damping. What you can see here in this figure is Fourier transform spectral power plots that indicate that the spectral power at any frequency is inversely proportional to that frequency. There's a couple cool things in this. These are long-term data. You can see at the 1-year time scale, there's a real peak in spectral power. What that means is that one of the dominant signals in these time series is an annual signal, which is super useful for prediction. The other dominant signal is diurnal. You can see that at the sort of 24-hour. It's most pronounced for nitrate. But everything else is basically, there is no characteristic time scale of solute variation, which is a little bit problematic. It means that you need to be very careful about how you interpret trends, because trends occur at all time scales, and you need attributing those trends to anthropogenic change or to something related to a shift in the watershed can be quite difficult. So basically what we have is this sort of theory, and these are for very small catchments, that basically says that the stream is irrelevant. Everything that's happening that's coming out of the watershed is all about the watershed. It's all about the storage and release of water and solutes from the watershed. But that can't be the case. I mean, we've measured reactions in stream networks. We know that this stuff, many of these solutes are being reacted on by the environment. And so what we went to is we sort of said, well, the channel must matter. How could we detect the channel in this signal? And for example, why are we not seeing a channel signal here? Well, it might be because this is a super tiny watershed. So what would happen if we applied this logic to big rivers? And the idea is that in a big river, think, the St. Johns River, maybe that's the home river for you guys. The St. Johns River is a big river with very long residence time. The water sits in the network for weeks to months. And during that storage is being acted upon by the biology that's imprinting its signals on what comes out the bottom in Jacksonville. And we ought to see the imprinting in the spectral behavior of that sort of as a function of river size. And so the way to think about that is at some break point, we stop being about the hill slopes and we start being about the effect of the stream channel. So now we can start to isolate what the stream channel is doing, what the channel storage is doing vis-a-vis the hill slope. And when we did that, this is across rivers that span a huge array of the United States, all from sensors, by the way, right? So all of these are sensor-derived time series, and I'll give you a moment just to look at it, but in almost every case, there's a very strong slope break in these spectral power plots that suggests at some point, at some residence time, the signal changes from a hill slope signal, a fractal signal, to a much steeper damping signal that's characteristic of what channels do. And what's really cool about that is that break point is dependent on river size. And so what we're saying is embedded in the signal, there's all these hill slope properties that are embedded in the signal, but there's also the channel properties that are hidden in the signal. And so we can start to isolate those and start to attribute some of the timescales of variation to what's happening in the channel, which is super important because we want to try to deconvolve those two things. All right. So there's Yogi. Just take a quick digression here to talk about the springs. If you've never been to North Florida to see the springs, in my estimation, they're the best part of Florida. These ultra clear water, the clearest fresh water on earth, comes out of these karst caverns, and it is the water chemistry, the water temperature, the flow are remarkably invariant. This is actually real data showing temperature, specific conductance, pH, and nitrate. So they deployed a high frequency hourly sensor at one of these spring vents, and it was, let's just call it the worst possible place in the world to put one of these expensive monitoring networks, because it doesn't vary, right? The Florida aquifer is so big. The Florida aquifer is bigger than Lake Ontario. It's a gigantic aquifer. And so when it recharges, they basically damps out all the variation. What you get coming out of the springs is the long-term average. But if the top of the river, what comes out of the spring vent, this photo right here is the Ishtuckney River, the head spring of the Ishtuckney River. If it's constant, and I put a sensor downstream, well, now I have this ability to detect only what happened in the river because there is no watershed signal, right? The watershed signal has been removed. And because these systems are so clear, they're also extraordinarily productive. These are like almost rainforest levels of primary production. In fact, the first measurements of primary production in any flowing waters were made in North Florida, in Silver Springs. So this place has a legacy of teaching us about how metabolic systems operate and the coupling of photosynthesis to sunlight in aquatic settings. Very high primary production. And so we thought, well, listen, maybe we could put a sensor downstream and we'd see what's going on in the river. And so that's what we did. We put out oxygen sensors and conductivity sensors and nitrate sensors and phosphate sensors, and lo and behold, it's this beautiful dance of diurnal variation. You can see the heartbeat of the river is the oxygen. That's the black line on top. It's this almost ridiculously regular signal. This happened to be a period when there was very little rain. And so it wasn't even cloudy. So basically what we're seeing is the time series of respiration and photosynthesis coupled, productivity of oxygen during the day, consumption at night. This covariance, inverse covariance with conductivity, this is because these are very alkaline systems. They come out of the water out of the ground supersaturated with respect to calcite and aragonite. And so consequently, when the photosynthesis depletes carbon dioxide, you get precipitation. So you're actually removing minerals from the water every day. Nitrate has this beautiful sympathetic variation that's almost perfectly out of phase, which is to say the nitrate is depleted exactly as photosynthesis is turning on. We'll come back to that in a second. And phosphate is an even more interesting and curious dynamic, but it's also clearly diurnal. And so this, for me, was very much a sort of a win for the sensors, because all of a sudden we had this incredible sandbox in which to think about ecological processes. So nitrate is out of phase with oxygen, and primary production, gross primary production, total photosynthesis, is an excellent predictor of how much nitrate variation we get. And so I'm just going to show you some data. This is the nitrate and DO time series. The green flat line and the nitrate is the flow weighted input of all the springs, which is also very constant. So the river is an enormously effective reactor. This is a site 5 kilometers downstream of the inputs, and it's removed somewhere on the order of 30% of the nitrogen by the time the water gets there. We thought, listen, let's just sort of integrate peak to peak. The green area there, we'll attribute that to autotrophic assimilation. So that basically asserts that the autotrophs, the plants, only take up nitrogen at night, or during the day. They don't do anything at night. And when we did that, you can basically run an integral on that, and you end up with a relationship between gross primary production, which is basically the fixation of carbon, and the assimilation or fixation of nitrogen. You plot one versus the other, and you get a very strong relationship. We can explain nearly 90% of the variation in nitrate uptake with primary production. But you also get a slope, and that slope is the stoichiometry, the tissue stoichiometry. A tissue, everybody needs a certain amount of carbon, nitrogen, sulfur in order to grow. And the plants are the same way. They have a particular favored stoichiometry. That stoichiometry is on the order of, for the vascular plants, on the order of 25 to 1. And so we see at the ecosystem scale, the sensor is revealing that like that organismal tissue level coupling of carbon and nitrogen is revealed at the large scale. It's pretty exciting. What's pretty exciting for us, so I'm going to give this one a yogi because it was an epiphany, but it even got more interesting because we can sort of think about the remainder of nitrogen retention and think about like what are the processes that might have led to the river being so effective at removing nitrogen. It certainly wasn't assimilation. We just showed that only the wiggling is the assimilatory part. So there has to be other processes of nitrogen removal. And so we took this very simplified version, not Theramont, what was it called? Theamox. Like basically everything that wasn't assimilatory reduction of nitrogen was denitrification. And we said, well, what are the things that control how far the peak of that green wiggly line is from the solid green line? That's the non-assimilatory nitrogen retention. So in this case, about 80% of the river's removal is this other process. And what's really interesting, so this is sort of the one way to think about it. We've got these upstream inputs and we can integrate to the peaks, and that becomes our dissimilatory or heterotrophic assimilation. And that assimilatory, that flux is not as good, but it's still pretty convincing that this is under metabolic control. It's basically total respiration in the system that's driving nitrogen removal. And if we look at it day to day, if I look at the 1 day change in primary production, which is basically making available a lot of bioavailable carbon that might fuel a heterotroph, and the 1 day change in denitrification, super strong coupling. And so we're showing that the the ecosystem metabolic forcing is coupled to the nitrogen removal at the long term, but also at this very short, daily time scale. So that one gets a yogi as well. We thought, okay, if it worked for nitrogen, we should try for phosphorus. So we put the phosphate sensor out. There's a lot of more complications in thinking about phosphorus because it has all sorts of geochemical interactions. I'm not going to get into how we did that, but you can use specific conductance to think about the absorption of phosphorus into newly formed minerals. So these are the signals. When you take the gray line is the raw data. If you take out the piece that was sorbed by mineral interactions, you produce a corrected phosphate signal. That's the black line. That's very strongly diurnal. But you'll note that peak phosphorus is in the middle of the day. So peak phosphorus reduction, the attenuation or assimilation of phosphorus, is happening at night. And at first, I sent the technician out like 3 times. I'm like, you got the timestamp wrong. Expect it to be at the same time, that primary production and phosphorus assimilation would be synchronized. They're not. We'll come back to that in a second. But if I look just at the uncorrected data, that's the gray line, there's pretty convincing evidence that the primary production is the control on the amplitude of that phosphorus signal. But when I get rid of the mineral interactions, so this is basically suggesting a carbon to phosphorus ratio of almost 1,000 to 1, which is really high. The vascular plants are about 480 to 1. The algae in the system are about 430 to 1. This is carbon to phosphorus. But when I correct the signal for these mineral interactions, I get a carbon to phosphorus ratio that's much closer to what I expected, and it lines up much more readily with the data. So we feel like, wow, all of a sudden now we're watching Redfield's ratio unfold in real time, not at the tissue scale, but at the aggregated, integrated ecological scale, which we're pretty stoked about. It gets a yogi as well. But we were left with this very curious thing, which is like, why on earth is phosphorus assimilation lagging primary production by somewhere on the order of 11 hours, 8 to 11 hours? Turns out that organisms need phosphorus mostly to produce new ribosomal RNA. That's the main, they use phosphorus in their ATP cycle, but that's not new phosphorus. That mostly is recycled phosphorus. And Jim Elser, who's a friend and colleague at Arizona State, he's showed, for a long time that this is the engine of phosphorus assimilation and needs by organisms is in the ribosomes. And it turns out that ribosomal RNA is produced maximally around midnight. And in fact, this Ashworth paper, which is a PNAS paper, basically showed that for these marine diatom, they upregulate phosphorus assimilatory pathways at night, and they upregulate nitrogen assimilatory pathways during the day. And so consequently, what we were curious, like we were sort of naively looking at this signal in this river and being like, what the heck on earth is going on? The biologists were saying, this is exactly what we'd expect. And so that it was revealed at the system scale, I think is actually a super cool thing. So yeah, this one definitely gets a yogi. I want to just take how am I doing on time?
11:35. 25 minutes.
25 minutes. Okay, I think we're good. If you have followed the controversy about the springs, the big thing that is going on with regard to management in the springs is this quite dramatic ecological shift that's been happening really since the 1990s. And on the left is sort of the archetypal expectation. H.D. Odom wrote a very influential aquatic ecology paper about Silver River. That's what he saw back in the 1950s. So sort of, if you know anything about like Lindemann efficiencies, like the birthplace of a lot of ecosystem ecology in aquatic systems was born in a place that looked like that on the left. Most places now look like the thing on the right. And there's a lot of interest in trying to understand that transition and you can imagine also remedy the transition. And the question is, well, why does it happen? And the prevailing narrative has been nitrogen enrichment, that basically we're contaminating the Florida aquifer with fertilizer. Nitrogen enrichment is prompting the overgrowth of algae, and that is leading to this state shift where algae becomes dominant and the vascular plants are essentially extirpated from the system. It is definitely true that the vascular plants have more or less disappeared from most of the iconic springs in North Florida, but the causal mechanism is still a little bit contentious. And I want to make a real brief case informed by those sensor data for why nitrogen probably isn't the problem. And the first is that those two pictures I showed you, the one on the left, that's how we want it to look, is in a place where the nitrogen enrichment is somewhere on the order of 50 to 70 times background, right? So there's a hell of a lot of nitrogen in Silver Springs, and it's maintained the character of an ecosystem that's kind of what we want it to look like. And the one on the right, which is a pretty luxuriant algal mat, and more or less everything else is dead. Well, that one is background levels of nitrate, and so it's so just operationally, it's very hard to understand nitrate as a control when you look at photographs. Of course, I could totally cherry pick the photographs. So here's a relationship between nitrate concentration on the x-axis and algal cover on the y-axis, and the correlation is kind of a unique thing when you do science, that the r squared is 0.00. So in other words, there's zero information of nitrate in understanding algal cover. We can think about that in the context of primary production, which is actually what we mean. We don't mean that nitrate stimulates algal cover. We mean that nitrate stimulates growth, which enables algae to outcompete SAB, but there's no evidence that nitrate is enriching and enhancing primary production either. And the organisms are telling us this, and they have been telling us this for years. If you plot most organisms, plants in particular, have relatively plastic stoichiometry. In other words, where you, humans, are a very precise recipe of different elements, and you can't change it. And if you do, you get sick. Plants are much more flexible, and they can kind of grow at whatever the environment gives them. But when presented with enough of whatever they're interested in, they'll grow at whatever their evolutionarily preferred stoichiometry is. And across all of the organisms that dominate this system, the relationship between the x-axis, which is the input, the nitrogen to phosphorus or carbon to phosphorus ratio of what they get, versus how they grow on the y-axis, is basically uncorrelated. There's no slope. Everything is growing exactly how it wants to grow, regardless of how much nitrogen or phosphorus is supplied, which means that they're like the people who leave the Golden Corral buffet, not because Golden Corral ran out of food, but because I'm not hungry anymore, right? That's exactly what's going on in this case. And so the organisms are basically telling us it's not nitrogen. It can't be nitrogen. It can't be phosphorus. It has to be something else. There is a very, very good story for what else it is, but I'm not going to have time to get into it other than to say that it's I was talking to Mike McCoy at Harvard Branch. This is a trophic cascade. What's happening in this environment is a trophic cascade, and it insists that our attention turn to interesting ecological interactions that have been changed in the springs, and it's not, strictly speaking, controlled by aquifer pollution. We should still fix that problem, but if we want to fix the springs, we have to attend to other. But why not? I mean, nitrogen is what causes the dead zone in the Gulf of Mexico. Nitrogen is what they're interested in the lower St. John's. Nitrogen is in the Indian River Lagoon. We have this notion that nutrients are super important for predicting primary production. Why would it not be the case here? And it basically has to do with economics, right? And so we can only populate these two things, demand and supply, because we have sensors, because now we understand what the ecological demand is and what the supply is. And so I'm just going to walk you through some basic ecosystem math, but we know that primary production in these ecosystems is really high. Works out to about 1,600 grams of carbon per meter squared per year, which if you follow the Whitaker biomes puts us, in a tropical forest level, these are the springs. The nitrogen demand is stoichiometric. I just showed you that. Like, I can predict how much nitrogen the ecosystem needs based on how much carbon it needs. And so that number is pretty fixed, and I can then take the amount of nitrogen that's coming out in the spring vent and spread it out over the entire river. In this case, this is an 8-kilometer river, and show you that the amount of nitrogen that's supplied to that ecosystem today is nearly 200 times what it needs, right? So it's basically using a little bit more than 0.5% of the available nitrogen. And even under historic consideration, under historic conditions, it was close to 7, almost 8 times the supply. And that assumes that there's no nitrogen recycling, which we can document is actually happening. And so that's why, is that the demand is relatively small compared to the vast supply that's provided. And so consequently, we need to be thinking about our thresholds for water quality management in flowing waters in a little bit of a different way. And I'm not going to skip this, but there's some theory that we can apply, take the sensor data that we have, both for oxygen and metabolism, but also for nitrogen and phosphorus, and start to understand what are some operational thresholds where a river ecosystem is nutrient limited, and what are some operational thresholds above which it's nutrient saturated. And that's a very important, somewhat pragmatic definition. Let's skip the
Does
details.
that not have to do anything with ammonium though, the actual form of nitrogen?
It might do. Ammonium is pretty low in these systems. If there's a recycling process, it'll be ammonium first. So ammonium spiraling may be quite high. But you know, I mean, one of the things that was really interesting about the those wiggles, and we did an integration, was that they're using mostly nitrate. Why? They wouldn't want to use nitrate. They'd much prefer to use ammonium. There's just not that much ammonium available. And so consequently, in the system, it's a nitrate source. It's a pretty toxic environment in general.
So that question is still out there, why the springs are becoming, why they're changing.
Yeah, I think there's some really useful sort of counter narratives to the nitrogen enrichment, mostly related to this trophic cascade that I was discussing. I'm happy to talk to you about it. It's a cool story. It just didn't fit. All right, so now I want to just change the reference frame. Everything to date has been a sensor sitting at a point watching water flow by, but you can do it the other way, where you apply a sort of pseudo-Lagrangian framework, which is to say you attach a sensor to a boat, in this case, a boat or a canoe or a kayak, and you sample longitudinally, and you try to sort of stay close to the velocity of the river, and that allows you to start to think about whether these ecosystems are spatially heterogeneous, or do we, as we've been assuming, they're sort of homogeneous. And I'll just cut to the chase. They're not. They're super heterogeneous in space, and it's an important insight that only could be made available from a sensor that can collect high frequency measurements. So this particular Suna was deployed to measure every 5 seconds. And so as we float the river, we're getting a nitrate observation every 5 seconds, which at the time I would say, and people would be like, ooh, you guys are hard audiences. Like, we do 5 measurements per second. Anyways, there's a lot of things you can learn by tracking water as it flows through the ecosystem. And in particular, so this is a typical longitudinal trace. You can see there's a little bit of noise. There's certainly some turbulence, right? So there's sorts of interesting scales of variability that nitrate is operating on, and we're sampling one of them. But the slope of that line is a nitrogen retention rate, and that nitrogen retention rate is super strongly related to the nature of the river. When the river is wide and shallow and highly reactive because it's sunny and because there's a lot of benthic surface per unit volume, the reaction rates, the slopes of those lines are really steep. And in the much narrower parts of the river where it's more shaded, the slopes are much more shallow, which is totally consistent with theory, but you could never see that until you were basically tracking a longitudinal profile like this. And so we've done this for a lot of different rivers. We've done it, we call it the first spiral because the water comes out of the ground and it's just constant. And everything that happens subsequently is sort of the ecosystem starting to imprint its metabolic and biogeochemical character on the water. In stream theory, that's called nutrient spiraling. And so we're basically watching the first nutrient spiral unfold. And so that one definitely gets at Yogi because now all of a sudden you can actually see it. You can watch it happen. But it turns out that this is actually a really thorny problem because a Lagrangian framework, strictly speaking, is you follow an individual parcel of water. But this is a turbulent environment where there's shear stresses. And so parcels of water are shearing past each other, and some are getting retained in what we call immobile zones, and others are advecting down the thalweg really quickly. And of course, you can't exactly sample with any small parcel of water because it's being stirred and mixed. And then moreover, depending on how fast you sample, like whatever your watercraft is doing, if it's the mean velocity or twice the mean velocity or the speed of light, which was one of our scenarios, right? You're basically sampling at an instant longitudinally. You get really, really different curves. I'll call your attention to the upper right curve, where at any instant in time, right, in a particular part of the day, because it's also varying, the whole thing is varying in time. You can see in the upper left, the profile you would obtain from this river, depending on when you started in the day, because the whole signal is diurnal, super rich playground of different signals to interpret. The one on the right is at any given time, depending on how quickly you sample, you get a whole array of different signals from which to be confused. That was sort of our initial thing. And our initial idea was that you could use these profiles to kind of extract ecological kinetics. How quickly do reaction rates respond to variation in concentration? But it doesn't work. You can't see it, but right on these gray and black lines, there's both a first order and a 0th order kinetic fit, and they're like indistinguishable. Most of the signal is the fact that as you sample, you're actually sampling different water all the time. So we're like, wow, that's kind of a problem, but maybe we also can like leverage that idea. So this is Rainbow River, which if you ever get to North Florida is definitely one you should check out. It's by far the best protected spring ecosystem in North Florida. And what we did was over the course of one day, we sampled in kayaks with, this is for oxygen now, from the top, that upstream sensor. So we had a time series, a sensor that was collecting an Eulerian time series at the top and bottom. And every hour we would shoot the river in a kayak and get these longitudinal series. And the idea was that the Rainbow River goes from the really beautiful meadows of grasses, vascular plants, through a period where a zone where they, did phosphate mining. That place has been denuded for 50 years or more, and it looks a little bit like the picture on the right. And so as you go downstream, you have this longitudinal gradient where it looks really good at the top and it looks really like bad at the bottom. And so what we did was, well, here's up in the upper left is the theory. Here's what we would expect to happen. Each of the kayak traces, if everything was homogeneous at different times of the day. And you can see the lines are, they have different shapes, and they're basically because the craft as you sample is sampling different water that's been sort of exposed to sunlight for different amounts of time. And it's quite a rich problem to think about. If you take that's sort of a distance profile on the left. If you put it on a time series, you can, and the dashed line on top is the downstream sensor. The stippled line is the upstream sensor. So we started each kayak run at the upstream sensor, and we paddled down somewhat quickly for the downstream sensor. And what we would have expected to see at each one of those profiles over time are those different colored lines, right? So it's pretty cool because that's more or less exactly what we saw, right? So we can sort of reverse the reference frame, and instead of thinking about the signals in terms of their time series, we can think about them in terms of their spatial profiles. And we understand enough now to interpret those. And so the graph on the lower left is the spatial series that we extracted from these kayak profiles, and on the right is the time series. And you can see they align with theory pretty well, which would suggest initially that, hey, the Rainbow River is pretty homogeneous. But every one of those profiles, you have a model prediction, which assumes a homogeneous environment, and then you have what you observed, which is, well, it's probably not a homogeneous environment. And at each location, you can detect an anomaly from your model. Like, how bad was your model? That's what the solid black line is. And so we take every one of those profiles and we plot the anomalies. We get this plot. So this is basically what we call the metabolic anomaly. This is suggesting that in the upper river, there was way more net ecosystem production than the model predicted. And in the lower river was much less. And that is basically how much metabolism is happening, but we can disaggregate it over the whole river. And when we plot that against our census of the submerged vegetation, it's like, holy, that's pretty cool, right? It basically is, we can suggest that there are simple proxies that we could obtain that would predict the spatial variation of the metabolic process in this heterogeneous river. And so I don't know where Yogi went, but I think that one deserves a Yogi.
So when you say model prediction, so we're talking about a physical model, right? Not a linear regression.
No, it's a numerical model, a hydraulic. I mean, it's very simple, but it's a hydraulic model, one-dimensional, and it has to account for things like sort of advection, dispersion, and storage, but it also has to account for gas exchange, which is the big thing that controls oxygen dynamics. So this last sort of sensor example is, we're like, well, it'd be really useful to try to further isolate the river into individual elements of the river. So what we did is we built these Lexan boxes. Pretty favorable environment to do this because the sediments are pretty fine grained. You can insert a box pretty easily into the sediment. They're not that deep, and so if your box is tall enough, you can have it open to the air, and so you get rid of some of the artifacts of changing the excluding oxygen exchange. And we put oxygen sensors, nitrate sensors. For a while, we even had a phosphate sensor in one. The idea is that you can start to interrogate the ecosystem using experimental treatments that would be impossible at the whole system scale. And in particular, once you isolate this little parcel of the river bottom from flow, all of a sudden you get you get natural attenuation, you get depletion of this of nitrogen in particular, which gives you a clue about how the river ecosystems are using that resource. And then you can do other cool things, which we haven't published yet, but we've put grazers in one and not in another. We altered the temperature, we altered the sunlight. This is like now an experimental unit that we're quite fond of. We've done about 200 deployments so far. We've published 2 papers on this. These are all, like I said, this is probably not amenable to every place, but it would, it could work in a lot of the Indian River Lagoon, for example. And we can see in the places where there's dense submerged aquatic vegetation, there's about the same amount of sunlight between the two, but way more oxygen production in the dense one, translates into much higher primary production in the dense one than in the bare site. We see much more rapid depletion of nitrogen in the dense than in the bare. And we can then take that, do a little bit of math with that declining nitrate signal and partition that nitrogen retention into uptake and denitrification. So that's pretty cool. And we can do that in different places and at different locations within the river. And what we get are these long tailing behaviors. All 3 of the ones on the left, Silver River, Rainbow River, Gum Slough, are all really nitrogen enriched, right? Their background concentrations in the Florida aquifer 100 years ago were probably 0.05 milligrams per liter. And almost all of them are sitting well above 1 at the spring vent. And so we're looking only, except for the one on the right, only at enriched nitrogen settings. But Alexander Springs Creek is in the Ocala forest. It drains the place that's only forest, and it is one of the few springs that has sustained very low nitrogen concentrations. What's super interesting about this is that if you look at the time series, what you get is assimilation, uptake of nitrogen in the day, in the boxes, right? You can see the peaks are basically highest in the daytime. Alexander Springs is completely backwards. It inverts the whole signal, which is suggesting that the nitrogen cycling at this place in Alexander Springs, where there may be nitrogen limitation, is actually quite different than these other places. So then what we did is, well, what happens if we introduce new nitrogen, add nitrogen to the Alexander Springs setting? And while we add nitrogen, first of all, the nitrogen disappears super quickly. This ecosystem is primed to assimilate a lot of nitrogen. But when nitrogen is abundant, the nitrogen is peaking. Nitrogen uptake is peaking during the day. But then as soon as the nitrogen goes away, the system reverts back to the way that it was. And I think it's just this really quite lovely clue that you get about how these ecosystems respond to variation in space and time and the solutes that force them. You can take those data and you can fit a series of varying complexity models. These are regression models where we're but these are theory-derived regression models where we're fitting basically the bottom right is the most complicated, where the total uptake is a function of primary production and some uptake kinetics. We can also apply a sort of first order kinetic model to that, or we can apply this ND term here is the kinetic order of denitrification. And the models do a really good job of matching up with the observed data in almost every one of our deployments. And one thing that we can do then is start to say, well, what is the kinetic order of these different reactions? Assimilation, which is the uptake of nitrogen, in almost every model that you look at in any river is treated as a first order process. In other words, more nitrogen is assimilated when nitrogen concentrations are higher. But that is absolutely not what's happening. Nitrogen assimilation is a zeroth order process. It doesn't matter what the nitrogen concentration is, at least in these systems. And the reason is that a nitrogen is abundant. But denitrification, which is the other process of nitrogen, is first order. It basically is a first order, a little bit less than first order. The mean kinetic order is 0.87. And so it is very much concentration dependent. And so in terms of making predictions about how these river systems attenuate nitrogen as water is transported through them, this gives us a really important clue as to how we would parameterize that model. I suspect that I'm running out of time, so I'm going to skip to this. So this is some of the most recent work that we're doing, where we're really trying to think about sensors versus sites. This is a paper we just published this year. It was massive effort. It's a curated data set, a benchmark data set of loaded chemistry across CONUS, all 48, lower 48. It's a 20-step process to curate the data. It's meticulously kind of coded and repeatable. Ends up with 34 million data records across 286,000 sites in North America. one of the cool things is every site now has a hydrography, like it knows where it is in a river network, and it knows what the watershed that made it is, like what is the forest cover or urban cover. So it's a playground now that all of a sudden I think is enabling a lot of AI applications to try to inverse model this very complicated problem of why is the water quality good in some places, bad in others. I'll note, this is something that I'm very proud of. 25% of all those observations are in Florida. Our state has made incredible investments in water quality, and I think we should be thanking our decision makers for. This is the curation process. Every single entry that came out of the National Water Quality Portal, which is, by the way, not all the data, but that's all the data that we did for this particular benchmark data set. But every single one of them was modified in some way. About 40% about 33% of them were thrown away for various criteria. This is the map of the data. It's interesting because there are some places with only one observation ever. There's other places where there's thousands and thousands of observations. It's a very interesting smorgasbord of different observations. But one of the things that we were very interested in, like we published the data, so you can go download the data and use it and do whatever. But we were more interested in trying to understand what is the variability of the water quality that we observe. And this was a hypothesis. This is the NSF funded project. This was our hypothesis that basically most of the things that we measure in river systems are more variable in space than they are in time, right? Water quantity, which is that blue dot, is much more variable in time than in space. And so what you're looking at here along the x-axis is the coefficient of variation in space. So it's like the coefficient of variation of the means. On the y-axis is the temporal variability, which is the means of the coefficients of variation. So they're the same units, but they allow a sort of unitless comparison of which is more important. And one way to interpret that is that red line is equivalence. And if you're on the north side of that red line, you need more sites or more sensors. If you're on the south side of the line, you need more sites. And what we're showing in the data is unequivocally support for that. And so we're spending, 2013 was peak water quality sampling in North America. Since then, it's dropped by about 50%. Big change. Why are we doing that? Part of it is because I think our appetite for spending that much money on water quality is maybe going way up. Part of it is that we are spending a lot more money on sensors. And this would suggest that for most of these solutes, that's probably not the right call. That spatial variability within river networks is by far more important than temporal variation. So when I heard that Bing, who's built a drone that can go sample oxygen in lots of different places, that is the sensors that I would argue we need for the purposes of our interrogation of our national water quality situation. All right, so there's a yogi. I'm going to skip this and just cut to the conclusion. So we can observe a lot by watching. Sensors have been eye-opening for me as a user. I'm not a fabricator. I'm not a data scientist. I'm more of a sort of ecological theoretician. But we have these new scales of solute measurement. We can do Eulerian sampling at high resolution. We can do Lagrangian sampling. We can now do experiments where we track the dynamics of ecosystems in response to our manipulations. That's enabled a whole bunch of new inferences about watershed functions, about how solutes are retained in river ecosystems that are somewhat pathway specific, which I think is super useful. There's experimental manipulations that we can do that allow us to interrogate the effects of things like grazer interactions or toxins. And we can think about variance patterns, and we can try to use those variance patterns to be more economical and efficient with regard to how we measure our water. Ultimately, why are we collecting all these data? It's because we want to understand our ecosystems better. We want to understand the systems that we're interrogating better. And so I think the challenge for everybody in this space is not just to collect the data, but to collect the data for purpose. A reason why is to develop new theory, to develop new thresholds, operational thresholds, to develop new predictions. And I tell my students all the time, more data is not better. More data makes your life more complicated. You have all this, you have a mess to deal with. But if you can put those data in service of developing new theory, now you're building knowledge. And so I want to just then close with the Flow Center and this vision for what I think would be a great partnership with iSense, with FAU more broadly, and with the state university system. And that is that we have a ton of capacity. I can't tell you how impressed I am by just touring around the last 2 days, but also the conversations that I've had with Jordan and with others over the during the development of this proposal. Like, we have a lot. This is a great university system, and we're not duplicative, but we are. I think there's a lot of synergies that have gone unexplored, and I'd like to see that resolved. We have, I think, to deliver on the promise of all these data that Floridians have paid for over the years, making sure that it's all readily available and that users have access to all forms of these sensor data. That is like one of the hardest pieces of that puzzle, and I hope that we will be able to contribute in that space. I want to develop this as a convening space. I think that's one of the pieces that I think will make us better collaborators and more responsive to the state's needs. Building an expert database that isn't boutique to the University of Florida. We're trying to make sure that it has the capacity to reach out and capture the expertise that exists at other institutions, not just universities, but outside of it too. And so this sort of expertise database is a big part of it. And then ultimately we're collecting the data because we want to solve problems. We want to develop new understanding. And that thought leadership piece of the Flow Center, I think, is one area where there's a lot of opportunity for academics to really show how we're worth it to our funders. So that's it.
We have time for maybe one or two questions if anyone has any. On Zoom, feel free to unmute yourselves if you have a question.
Yeah.
Thank you so much. Excellent presentation. One question I had was, you have these boxes. How much is the interference from the box towards the actual signal with respect to sensors? Do you see any effect of that box?
Interference in the sense of the sensor being like the actual digital signal, or I mean, we shut off flow. I'll just answer it like directly in some way. Like we shut off flow, that's very different, right? That little piece of the river is now different. The turbulent structure is gone, the sort of evacuation of all the, it's not mixed. And so that's a thing. In fact, one of the things we learned really quickly is that we had to use fish tank pumps to circulate the water in there so that you didn't stratify and start to alter the river. So yes, I mean, I think there are some effects like that, but in terms of sensor interferences, we haven't noticed it.
No, the natural environment being disturbed by the boxes. That's what I meant.
Yeah, not really. It is an invasive process. You have to insert it, but so we basically discard the first day of data every time we deploy a box, and then we get usually 6 good days of data from each one. So yeah.
I'm a hydrologist. I work in water. The other question I had was, you have all the sensors measuring in space and time. So, I mean, most of your relationships are built in time. Have you noticed any other data sets where you have processes occurring some time back and they are influencing the processes right now? So you have this Granger's causality, that won the Nobel, economics. So do you see that kind of relationships? Have you built in your research in that situations?
Yeah, the hydrological system of the Florida aquifer is full of long lags, legacy effects.
Yeah.
Even understanding those lags is pretty tricky, but there's pretty strong evidence that the aquifer is a bladder that shrinks and swells over sort of multi-decadal timescales. And so when you are measuring flow, for example, and trying to relate it to rainfall, it's not, it's a tricky problem because the actual control volume of the aquifer is dynamic. And those kinds of lags are embedded in all kinds of things. And there's a lot of literature about legacy effects with regards to nutrients. I mean, Lake Okeechobee is a great example. There's probably 50 to 100 years of phosphorus stored in that system that, like, even if you turned off every current anthropogenic source, there's a long lag before you start to see water quality improvements. And I think attending to those lags is more important than just like measurements. It's really like calibrating our decision makers to be prepared for not having a lot of success for a while.
Yeah, thank you so much.
Yeah.
Okay, yeah, so thanks for the great talk. And I was wondering, and I'm not from this sensor field, right? And then I'm more from the data or AI side, right? In your opinion, what is the major barrier? Is we need to produce a better sensor and then better granularity or better timing? Or it's more about the understanding about these physics systems and how do you understand sensor data, in your opinion?
Well, the thing that I'm good at is not the sensor development. And so I'm going to say the thing that we need more of is what I'm good at. I do think that it's a little bit of one of those things like you need both ingredients in good measure, right? You need people that are thinking about how to actually make sense of the data, right? And apply maybe simple conceptual models to interrogate the data and do the observations comport with our expectations or not? And that's the I mean, very much the purview of academic science, right? That's what we do. But I am the beneficiary of some sensor engineer that commercialized and made available, tech that made new measurements available. And so I think there's a real strong synergy between those two enterprises. So I don't think any one of them is the key ingredient. I think you need both. And I'm increasingly intrigued by the third leg of that stool, which is that it's not just the interpretation of data in sort of a classical hypothetical deductive framework. It's not just that. A lot of our data are, I think, very complicated. They're uneven in time, they're uneven in space, and they, I think, require a degree of pattern recognition that isn't a person, right? I think that leveraging AI tools to extract sort of inductive reasoning, I think is a really huge part of it. I haven't done a lot of it, but I'm starting to collaborate in that space. And so I think that's another piece of the puzzle it's synergistic. It's not one or the other. I think you have to have sort of all of them all at once. And I think that's a little bit what I've been hearing about iSense that's so cool is that like you guys have a user community. You have users like people interpreting data here, but you develop these I don't know, sort of symbioses with users outside that are, so you guys have become the experts in terms of facilitating access to high quality, high frequency, unprecedented data. Somebody out there is asking for that, right? Somebody out there is going to use that. And I think that synergy is super important. It's been super important for me because all these sensor things are sort of whatever. I get how they work, but in terms of like developing them de novo, no way. I hope that answers.
Yeah, thanks.
Yeah, kind of a general question. How do you, in general, define your sampling rate if you are operating in the time domain or the space domain? Do you use any scientific methods? Are you limited by your hardware, and that's how you go about it? Obviously, the resolution is in certain cases very important for you to understand.
Yeah, it's a great question. In every case, it's been the baseline is the instrument, right? So nitrate sensor can measure about 0.5 hertz twice second half. We didn't run it at that because it ends up chewing through batteries super fast, and it was kind of like, we don't really need that. So we went with something that's like an order of magnitude less frequent. But we did ask the question, what's the autocorrelation structure of an observation? Because what you would like is to sample, and each sequential sample is new information. It's not just the same information at the time. And so we played around with that a little bit. I'd say in the end, we just, we didn't get too rigorous about that. I think for the oxygen, the story about the Rainbow River and the kayaks, like that sensor, for reasons that I'll never understand, but they basically don't allow you to take a measurement but every minute. So we thought that's too coarse. Like we wanted it to be more frequent. That was a constraint of our gear. There are other sensors that could do it more frequently. I think it's a really interesting question. I think that question isn't just about in the Lagrangian sense. I think it's in any sensor application. Many of my colleagues will measure who do metabolism work. They'll measure oxygen every 5 minutes. Man, you're just chowing through battery and sensor like the consumables. And, is that necessary? I don't know. I mean,
if you get a sense of an estimate of the rate of change of what you measure, then you can make claims about approaching Nyquist sampling.
Yep. That's exactly it.
But without that, I mean, we're in the blind, right?
That's right. So in the Fourier transform work, one of the things that we noticed is that many of the sensors are running at very high frequency, and at some point you reach the Nyquist frequency, and you basically are in white noise. And so at that point, you're basically sampling electronic background, and so that clearly should be, less frequent than that.
Yeah, thanks.
And we can just take our very last question from the chat.
Okay. I think the answer to the question is like unequivocally yes. All of the nitrate sensors that we worked with were initially developed as marine instruments. There's a little more interference because the nitrate absorbance happens at the same frequency as bromide, and so there's some corrections that the vendors do. But yeah, I think I think doing it in tidal channels. There were some colleagues at the USGS that have been doing a lot of work at trying to understand sort of nitrogen and carbon assimilation in tidal exchange channels, and they've published tons of papers about that. And so I think the answer is yes. I don't know. Biofouling is an issue for us. For folks that work in marine settings, biofouling is an exponentially worse problem. And so I think that's probably where most of the constraints will be. Yeah, it's a good question.
Can I ask one more question, just kind of relevant to the iSense audience? Your last recommendation that we need more spatial sensors. What does that look like from, say, a local perspective and say, like iSense, right? If we're developing low-cost sensors, have capacity to do both, say, high-frequency sampling and then deploy them spatially.
Yeah.
You know, can you go from your recommendation to a specific prescription, let's say our area, you know, based on capacity for sensor frequency and I guess even cost, like how do you make that bridge?
Yeah, I think that's the like monitoring network design question, which I think it's a really good question. And we are saying that, you know, the emphasis on sensor deployments at the mouths of big rivers so that you get high frequency data of, you know, watershed outlets is actually counterproductive. It's leaving all sorts of, like, if you have a fixed budget, that's not what you should do. But what you're describing is the deployment of low cost sensors strategically through a network. So you're getting both high frequency observations, but at many locations. And I think, you know, that's the, you know, the tech frontier is to enable those trade-offs of space and time to go away. You don't have that problem because you're not trying to deploy a $60,000 sensor platform. You have a $600 sensor platform, which you can replicate in many, many more places. So now you're checking both boxes, space and time. And I'd say that that's one answer to the question, which is that it, like, as the tech evolves, I think that answer to that question will evolve with it. In terms of like the local, what is the variance structure of Indian River Lagoon vis-a-vis sort of the St. John's River, vis-a-vis, you know, the Apalachicola River. I think I think that space-time variance framework is actually totally customizable to any place, and it would give you some guidance on what are the things. I mean, most estuarine environments are, you know, the answer is yes if you're trying to figure out whether it's spatial or temporal variation that matters. This is peculiar to river environments where we think you know, most of the variance is in the, you know, the sort of that each little stream samples a different part of the watershed, so it generates all this spatial heterogeneity. So I think, but is that true in the St. John's River? I don't even think I know. And so, you know, it might be that it's a different answer here than it is at continental scales, right? And it's almost certainly a different answer in an estuarine sampling environment than it is in a watershed environment. So I think it's more of a framework than an answer at this point to trying to answer that question. Like, what would be the appropriate sampling regime? I'm trying to maximize the efficiency of scarce resources given and given the problem I'm trying to address.
Again, a Nyquist sampling rate question, right? That's right.
The same
Space
thing,
domain.
yeah.
Exactly.
Well, thank you everyone for joining us, and thank you so much, Dr. Cohen.
Thank you for the invitation.